Welcome everyone to this webinar as part of the Construct Innovate Webinar Series. Today's webinar is on the design and operation of facade systems for better indoor environment. And today's presentations include the design of the integrated facade design for Atlas building, and that's going to be presented by Peyton van Mierlo from Valster Simonis. Peter is the consultant and regional director. The second presentation will be by myself. I'm Magdalena Hajdukiewicz from Eindhoven University of Technology and also a director of Construct Innovate. And my presentation will be on the investigation of indoor environmental quality in the Atlas building. And our final presentation today will be on climate adaptive building shells. And the speaker is Dr. Roel Lunen, assistant professor at Eindhoven University of Technology. So without delaying now, I'm going to ask Peter to share his presentation. Enjoy the webinar.
Magda, and I will share my screen. So I'm going to talk a little bit about the Atlas building and the way we designed the facade systems and integrated it with the HVAC systems and the climate control BMS. The Atlas building is the main building of the Eindhoven University of Technology. It was renovated in 2014 to 18, where we started with the renovation of the building. So you can see here that the original building, it was built in 1963, and it has a few special features, meaning that there's a little limited floor height to really bring the building up to today's code and today's building quality. And it also has an architectural importance or significance. So the look of the building with all this glass still had to be maintained. The building is 13 floors with 2 underground and a gross floor area of about 42,000 square meters. And as a goal for the renovation, the university required a sustainable building, which could be used in a flexible way and create a healthy environment for the people occupying it. And so we came up with this building concept to really reduce the energy load. We used energy efficient LED lighting, and this is commonplace now, but back when we started the design in 2014, it was still quite something which wasn't used on large scale renovations. The building is also connected to the thermal energy storage system. So we store the energy from the building that's excess in summer and release it in the winter. We're using climate ceilings to use radiation as well as convection for optimal comfort in the building, and using a complete fresh air system without recirculation, but we're using various forms of energy recuperation as well as solar power generation to get the energy use of the building down. And all the excess energy that's still required is using green power. But this still means that if you want to have this high quality of building, you are going to lose a lot of energy. So we looked in first place at the facade to reduce this energy load. And together with the architect, structural engineer, and building physics consultant, we came up with this facade system. The facade system consists of about 3 meter high, 1 meter 20 wide glass panels. And this is all along the facade. So these are triple glazed panels with argon-filled cavities, which give them a UG value of 0.5. And together with the frame, the U value is 1.1. The facade is also very sun reducing, so it has a very low G value, 0.26. But all this together means that the facade is quite heavy and quite big. The whole panel is about 5 centimeters, 50 millimeters thick, with the height and width of each panel, you can imagine it's quite a load. So the challenge was to have operable windows in this facade, and also windows that could actually be used by occupants even on the 11th floor. So what we did here is we used parallel windows which come out of the facade completely parallel to the facade itself, and using 4 scissor hinges which are electrically controlled to open the window because it's too heavy to do manually. And this actually provided us with a few benefits in ways to use natural ventilation, because even at higher wind speeds or winds that are directly aimed at the facade, you could still use operable windows to reduce the heat load with natural ventilation. And this facade, the openable areas, can be used to use flush out strategies, which are being developed. And we have also 2 positions at which a window can be opened. And this is because of safety requirements. So during daytime operation, the windows can be open 13 centimeters. So this is enough to have an opening on the sides, but no opening at the bottom. So this means that nobody can throw stuff out, or no limbs can get stuck under the ridges of the panels. And in nighttime, when the building is not in use, so between 11 and 7 in the morning, the windows can be opened another 11 centimeters. So we can maximize the use of nighttime free cooling. And because of this strategy, we also have to require the building to use an open door policy. So the doors to office spaces aren't normally closed unless somebody really requires the privacy. And this whole facade system, like I said, it's been electrically controlled, which also means that you can design it in a way where it can be BMS controlled and monitored. So we know from each panel if it's open or closed. And it can also be centrally closed by the BMS system, in addition to being controlled by the users in each space. And the ceiling of the facade is integrated with the climate control and lighting. So when the sunscreens go down, the lighting is changed automatically to provide more artificial light. And when the window is opened, the contact sensor on the window deactivates the climate ceiling, because basically you have an open connection with outside, so there's no use in climatizing the room. So it actually expands the bandwidth of the temperatures allowed in the room to such a degree that the climate ceiling won't be activated. Only when the window is actually closed will the climate ceiling be activated. And because of safety features and overheating, to prevent overheating of the building, we also have automatic overrides in case of wind, rain, maintenance on the facade, or high solar irradiation. And another option which is implemented and still being developed is the use of weather forecasting to either open or close the windows earlier to prevent any rain coming in, and not waiting for the rain sensor to actually detect the rain, or being able to predict that the nighttime cooling will be efficient, so you can open it maybe an hour earlier and already have the building cool off in the nighttime. So here's a little bit what it looks like when the windows are opened. And with either sunscreen on the higher parts or the lower parts closed. And this really helps reduce the amount of energy that the building needs. So in the summer, we can use a lot of natural ventilation and cooling during the nighttime to flush out excess heat from the end of the day, especially since the building is orientated east-west. We have a lot of sunlight still late in the evening on the building, even when most people have gone home. And instead of having to cool it with the ATES system, we can just use natural ventilation during the nighttime to flush out all this excess solar heat. And the nice thing about this building is also that it's been designed to be developed upon. So the facade system is built, it can be controlled, but there's also research, which is Magda's area, done on which kind of operational strategies can be used, and research also that has been done in the past on can we predict at which wind speeds and at which wind directions which windows should be open. So can we design a control strategy where we can detect which wind direction is prevalent and adjust which windows will be open to maximally use the natural ventilation potential of this facade, and to help the building learn which strategies work best. This is in a short overview of the building and how we really made the facade an integral part of the HVAC system. So those two work together to provide minimal energy use while still providing a high indoor comfort. And that was the last of my slides, Marta.
Thank you very much, Peter. So I'm just going to share my slides. I'm just going to follow on from Peter's presentation on the Atlas building at Eindhoven University of Technology campus, and show you one of those research projects that Peter mentioned. And this one is a EU-funded facing project on the innovative dynamic facade system for indoor environmental quality. So just as a brief introduction on why this research is important and why do we care about facade system, about energy efficient buildings. So buildings in general account for about 40% of the total final energy consumption and about 36% of the greenhouse gas emissions. And this makes them one single largest energy consumer in Europe. Also, almost 75% of the European building stock is energy inefficient. And different countries have to decarbonize their building stock by 2050. And there are different intermediate targets set by each country. And those targets are generally 2030, 2040, reaching to net zero by 2050. Occupant behavior and preferences are very important, and they contribute to the gap between the predicted energy performance and actual energy performance of buildings. We spend almost 90% of our lives indoors, so it is important that our buildings are not only energy efficient, but they also provide safe, healthy, comfortable, and productive environments for the occupants. This is a similar image to the one that Peter showed you. Atlas building, naturally ventilated glass facades are very common in the energy retrofits of large-scale buildings. They are architecturally aesthetic, they provide energy efficiency, and that's why they're so popular. So here you can, on the left, you can see a picture before the energy retrofit in 2019, and post retrofit on the right-hand side with the new facade. So now, just to show you the facing project that I'm going to talk about. So it focuses on this facade system. It's a dynamic facade system with a parallel window opening, where the facade is can be controlled by the occupants of the building, but it also reacts to the outdoor weather conditions and indoor environmental conditions, as Peter mentioned. So what the research project is doing, it's combining the measurements in the Atlas building with the qualitative user feedback. So those are the surveys capturing the perception of the occupants of the building with computational simulations. So in this case, a computational fluid dynamics simulations, but there can be also building energy simulations. And combining those three elements, we are looking at the airflow and heat transfer through the facade, and then how it impacts the indoor airflow and heat transfer within the indoor spaces and their quality. And next, how this impacts the energy savings, but also the health, comfort, and well-being of the occupants. So the objectives of the project, the high-level objective is to develop new operational strategies and designs for building facade system. And we want to ensure that the indoor environment is appropriate for the occupants, that the building-related health risks are limited, and that we reduce energy consumption. And within this project, by doing extensive measurements, we want to provide detailed indoor environmental quality parameters in offices. And we want to capture the perception of the building occupants of the indoor environment. So it's a point in time perception of the occupants. So we're not looking here at the statistical large data sets, but we want to see how the occupants interact with the facade and how they perceive the indoor environment created by incorporating that natural ventilation through the facade. And finally, we're going to use the measurements in the building to develop valid computation models of the indoor environment in the Atlas building. And those will help us to test those different operational strategies and see, can we save more energy, or can we make or provide more comfortable and healthy indoor spaces for the occupants. So this webinar series is about sustainability planning in construction. So I just wanted to link to the sustainable development. So this figure shows how the project impacts key EU and global challenges. The project addresses 10 sustainable development goals by contributing to the challenge of providing climate-friendly buildings that provide healthy, comfortable, and productive environments for people. The project combines interdisciplinary technical expertise, and that ensures the impact on the society in terms of health and well-being of people in buildings. And it also increases education and knowledge transfer, and that's done through the collaboration with industry. So in terms of the methodology, what we are doing in the project, so you've learned about the Atlas building from Peter's presentation. We take the building and operating building as it is and apply very detailed measurement campaigns. So we put in a lot of sensors in 2 offices that are naturally ventilated through the facade. It's a mixed mode ventilation because there is a mechanical air supply as well. But what we are interested in is look at the impact of that natural ventilation through the dynamic facade. So we put in a number of sensors in the offices. There are 2 offices. One is east facing, the other one is west facing, to see how the external conditions influence the internal conditions in the rooms. And then based on those measurements and using those measurements, we can validate computational models. So in this case, we will be doing computational fluid dynamics simulations similar to some of the research that has been done at Eindhoven University of Technology previously, but also looking at the building energy simulation when we take a whole floor of the building and look at the different ventilation strategies for looking at the larger scale of the whole floor. And to finalize our analysis, we also capture the feedback from the occupants. So we want to see, we know what are the measurements, we know what values we are getting from the sensors, but we want to see how those align with the perception of the occupants of the indoor environment. In terms of the measurements, we capture air temperature, indoor air temperature, air velocity, relative humidity, CO2 concentration, which is the proxy for looking at the air quality of the indoor environment. And then we also need boundary conditions for the CFD model, so air temperature, air velocity, and the weather conditions. And in terms of the surveys, we ask occupants twice daily during the measurement campaign, different questions about first some kind of background questions to see, you know, anything about their what kind of occupants they are. So we want to know their gender, their age, their disability, their general preferences in terms of the thermal comfort. Then specific questions on the thermal comfort, how they feel at the particular time. Are they too hot, too cold? Would they prefer to have the window open or closed? Do they feel the difference between their feet and their head level? Things like that. In terms of air quality, we're looking at how satisfied they are with the indoor air, with the quality of the air. So is the ventilation enough? What is the smell? What is the freshness of the air, etc. And then the general comfort, so some other factors for indoor environmental quality, such as the lighting comfort or noise comfort, if they experience any health symptoms, or does the indoor environment impact their productivity. So here you can see a plan of one of the offices. It is the east-facing office. At the top, this is the glass facade with the openable window. The yellow it's the furniture marked, and then you can see red and green. Those are the positions of the indoor environmental sensors, and we measure those at 3 different heights: at the ankle level, the waist level of the standing person, or head level of the sitting person, and then head level of the standing person. And here I just want to show you a few examples of the results that we are getting. So here are the indoor air temperatures. This is for the 21st of April. It's a typical working day between 9 and 6 p.m. Where the occupants were also asked to fill in the survey. And then at the top of each graph, you can see little marks for showing the time of filling in the surveys. The orange background shows you when the window was open. On that day, the occupants could operate the window as they wish. So whatever way they felt comfortable, they could open or close the window if the external weather conditions allowed. On some of the other days when we did the measurements, they didn't have that control, and we definitely saw an impact of having or not having control over the windows. So you can see the temperatures in general, especially in the morning, exceeded the ranges that are recommended of operative temperatures between 20 and 23 degrees. Now, what you can see here is the indoor air temperatures, but we can say that the values between 20 to 23 are those recommended by the Dutch building code for offices as comfortable. Especially in the morning, the globe temperatures beside the window were very high, and they definitely caused some discomfort to the occupants. The highest variability of the measurements was shown at the location of the sensors beside the window, which is understandable. There was some variability, the PMVD as well, but not as high as the one beside the window. In the morning, because it's an east-facing office, you can see that the temperatures were very high, and later on in the later slide, you'll see that the occupants felt that they were a little too warm at that time. Here's some results of the indoor CO2 concentrations. also shown the times when the windows were open and closed. So this is a proxy of looking at the air quality in the space. So the recommended ASHRAE guidelines for CO2 concentration in offices is below 800 ppms, and that wasn't exceeded in this case. So we can say that the ventilation rates were pretty good. And you can see, further analysis can be done on this, looking at, when the occupants were in the office and when they left the office, when the window was open and closed, and how that influenced the concentrations. We looked at the draft risks, so indoor air velocities, and again, the sensor that was located beside the window opening was the one that showed some risks of draft, where the turbulence intensities and draft rates were quite high. Now, in that room, beside the open window, there was no occupant located at the moment of the measurements, but there was a desk. So we can assume that if there was someone, they could feel the impact of that window opening. They would probably feel the local discomfort in terms of the temperature difference between the ankle and head level, as well as draft, and especially at the ankle level that is marked here in red. We looked at some correlations, so we wanted to see what is the impact of the air velocity coming through the window opening on the indoor velocities in the room. And for most of the locations, or almost all of the locations except one, there was no correlation, apart from the sensor that was located at the ankle level beside the window. There was a positive correlation, some positive correlation there. So using this kind of data, we can make conclusions and kind of investigate further parameters that are of concern that may cause discomfort of the occupants. So apart from the measurements, we looked at the occupants' perception. So they received a long list of questions twice daily, and they were asked to answer them. Here you can see just some extract of those questions. So at the top you can see some questions about the thermal comfort and air quality, and then some just general preferences on the of the indoor environment. And as I showed you earlier with the indoor air temperatures, the occupants in the morning felt slightly warm, and they would prefer to feel a little colder, especially the occupant that was located beside the glass facade. They all preferred the window open, and when we did some measurements on other days where we controlled the window, we noticed that when the window was forced to be open, the occupants preferred it closed, and when the window was closed, the occupants preferred it open. So we could see that from the responses, we could see that in general, the occupants preferred to have the control over the window. On those days when they had control, they felt more comfortable than on the days when they didn't. So just to summarize, we want to analyze and simulate the airflow and heat transfer through this glass facade in the Atlas building, and we want to investigate the impact of the space layout and also the occupant behavior on the indoor climate. And that will help us to evaluate the building-related health, comfort, well-being, and productivity effects on manipulating the indoor dynamics. And the overall goal of this project is to provide recommendations for facade system design and operation. So this facade is new. It's not very common to be installed in high-rise buildings. So we want to see how it is performing, and is there anything that we can are there any things that we can influence to make it even more efficient and more that will provide more comfortable conditions for buildings. Thank you. So I'm going to hand you over now to Ruel.
Thank you very much. I'm assuming you can see my screen now. So good afternoon, everyone. My name is Ho Lonen. I'm assistant professor at Eindhoven University of Technology. Here we have a pretty picture of our campus, but also actually illustrates what I'm talking about today. So in the back, towards the left, we have the Atlas building where we just saw the presentations about. So this building exists. It's now a living lab. And here in the middle of the picture, you see our outside testing lab for testing the next generation of advanced facades. So that's what I would like to talk with you about a little bit today. So when it comes to the building envelope, there are many requirements that need to be met, and sometimes they can be very conflicting. So to maximize the view to the outside, for example, that's generally the worst thing you can do when it comes to controlling the amount of solar heat gains and overheating. And in this way, we can think of many other conflicts, but actually at the same time, this also brings a lot of opportunities, or especially if we think about the fact that the weather is always changing. Also, the needs of the occupants inside buildings can be different. And this variability, we can sometimes take advantage of that. So around 15 years ago, actually, I started collecting an overview of what I called climate adaptive building shells on this Pinterest webpage. I think there's now over 500 different examples of buildings around the world that actually have been built, or some concepts, some ideas. And since then, I've continued working on these subjects. So another project I would like to bring to your attention, if this is something you find interesting to explore in more detail, is this European Cost Action Network that was called Adaptive Facades Network, where from different disciplines and different perspectives, all different elements, aspects of these adaptive facades were studied. And this also continued in a task from the International Energy Agency Solar Heating and Cooling Program, where particularly the emphasis was on building integrated solar building envelope systems. So really zooming in at what can we do with the sun in terms of photovoltaics and solar thermal systems to minimize the energy needs for heating and cooling, while at the same time optimizing indoor comfort. So in such projects, and also in the type of research that I do, we generally consider the indoor environment as what is the main thing that matters and what we want to try to optimize, but at the same time looking at all these different other interactions that are playing a role. Some projects we do this through monitoring and measurements. In other projects also simulation actually plays a large role. And here I would like to emphasize the potential of using these building energy simulations for product development of novel building envelope technologies. So the idea is that if we look at this technology readiness level, so the level of maturity of a certain technology, and then in the red line we have the resources, or the amount of funding that is available. Then typically for the more basic research, the fundamental science, there tends to be a lot of grants, a lot of subsidies available. And also when we move towards the market, so at the higher technology readiness levels, that's where we really see the potential for commercializing, and finally for putting successful products in the market. So that's also where we see a lot of funding. But in the middle, there tends to be this gap. And the idea, what I would like to show you later on in the presentation, is using these building performance simulations, how we can actually navigate, quickly jump from one technology readiness level to another by simply pretending that something is already possible or something works, even if it's not exactly there yet. And it can also mean that sometimes we can quickly identify that a certain direction is not really worth exploring further. But sometimes it can also really identify potential to really bridge this gap and help speed up promising technologies to reach the market. So what I would like to do in this presentation is go through two examples. The first one more focusing on commercial buildings, and the second one with a focus on residential buildings for now. So the first project, well, the inspiration comes from this building, or this idea actually, or the challenge of putting photovoltaics, so solar cells, combining that with glazed facades, with the idea that it can help balancing daylight levels, it can control solar heat gains coming in. But what you see here from this existing building is that, okay, we have that outer shell of solar cells, but at the same time, there is a need for roller shades, so for solar shading systems, which indicates that it's a little bit of a double solution to satisfy all the different requirements that are taking place. So with a group of PV cell developers, we actually came to this idea of customizing the amount of transparency and the amount of PV active material that we can have with such PV windows or solar glazing. So the idea is that we can have, depending on how much of the active material is there, by making these tiny thin lines of photovoltaic material, we can control the amount of view, the amount of light that is passing through, and conversely, the amount of PV electricity that is generated. And here the idea was to explore if we can then indeed eliminate the need for solar shading to mitigate glare effects. So the final solution, that project, we didn't go further than the prototype you see in the picture, but could, for example, look something like this. So what we did using simulations is then to have a different PV distribution percentage, or you can look at this as sort of PV coverage ratio. And then in the blue line, the negative points, we can see that the more PV we have, the more electricity we generate with the facade. I think that's quite an obvious result. But what we also see is that then the less solar heat gains are coming into the building, also the lower the cooling energy demand is. And to some extent, this is compensated with a higher need for LED, for electric lighting. And if we add all of this together, then we see that around the 70%, or in that region, that will be the optimum for energy performance in this case. So then we come to something around 30 kilowatt hours per square meter in this case. But what we were interested in further is not only to have the uniform transmittance, so what we see here in the top, but to play around with the position of where we have more and less active PV material, or more or less view and daylight coming in, with the idea that if the upper part is more transparent, that will bring also daylight deeper into the space, and that helps daylight comfort to improve. We can see that here in the figure that for a same uniform PV coverage ratio, we can actually increase the SDA, so the spatial daylight autonomy, the amount of useful daylight that gets into the space. So we can almost bump that up by a factor of where it would be 70 with a uniform. We would come to roughly around the 60 range in the ideal case here. So showing the potential for further design optimization with these different patterns. So now we are bringing this to the next level in a new project where we integrate these PV cells, but then make them bifacial so that they are active from the front and the back with a integrated Venetian blind system. So the idea is that when it's very sunny, the blinds close, some of the sunlight gets reflected and actually hits the backside of the bifacial PV cells. So we now have full-scale modules of this technology that will soon be tested. And at the same time, we are testing this on our outdoor laboratory facility where we have different PV cover ratios, for example, and different reflectance properties of the Venetian blinds. And here just a quick overview of that PV, well, building integrated PV and solar thermal testing site where we are analyzing all sorts of different technologies. Then the second example that I would like to show is for residential buildings and the motivation here. So this is a picture that shows the increase in heat waves and the extent of heat waves that we're seeing in the Netherlands. So the more orange and red it gets, it shows the warmer the summers we are having. And yeah, probably you are experiencing something similar in Ireland. At least that's what I was presuming. So the idea, or what we were playing around with here, is that if we emphasize more on thermal insulation in residential buildings, that works really well in winter, but has this drawback that in summer it can trap the heat inside. And what we are investigating here together with this company called Active Insulation is to see if we integrate this type of heat exchanger in an insulation panel. So we have this type of horizontal lines, and then here in the corner and in the other corner, it cuts through the insulation, and then this slab is sealed with aluminum foil. There is a small computer fan here, and if we turn it on, then we can basically short circuit the insulation. Or another way of thinking about it is that in summer night, when it's cool outside, we can actually expose the indoor air to that cooler environment. Or on sunny, cold winter days, we can actually bring the solar heat to the inside in a relatively efficient way. Again, we made a simulation model here and applied it to a typical terraced house building in the Netherlands for a well-insulated situation according to the current insulation standards. And then we are comparing this to a case where we have mechanical ventilation with different air change rates, and also looking at the combination with solar shading. And this percentages effective surface area, they refer to the amount of heat exchanging area that we have at the active insulation slab. Now, if we look at some results for thermal comfort exceedance first, then we see that in the base case, it's really far away from what we would prefer to happen. With night ventilation, we are well able to control the discomfort in summer. Turns out that solar heat gains are not the major issue here, at least the heat gains coming through the window. And also the active insulation is able to significantly reduce the occurrence of thermal discomfort in summer. How this is happening is, I can best illustrate it in this figure here, where we have the indoor surface temperature, and we see that with the green lines, we can actually effectively cool down the thermal mass after we switch it on here on the 14th of August. And we see that these lines are really drifting apart. So we don't only have the effect of flushing the air that we would maybe get with night ventilation, but really the sustained effect of cooling down the thermal mass. So that has an effect on the thermal comfort in summer, but we also investigated what does it do for the energy performance. So in winter, it helps to actively harvest solar heat that is absorbed at the exterior side of the building envelope, which leads to some reductions in the heating energy demand. And at the end, we also looked at, okay, this active installation needs electricity to work. We have these small computer fans that need to operate. To what extent is that actually influencing? And we can see those results here that, yes, it does add a little bit of auxiliary energy, but it's really at a much lower order of magnitude than what we would need to move around large volumes of air with a mechanical night ventilation system. So also from this perspective, actually, we saw a lot of positive signs of the potential of this system. Here we have some views of what it looks like in reality. So this is now being tested on this demo house. And in addition, in a European project with the name ZERAF, we are also testing this further, including also a solar shading system and the idea of using bio-based materials for the insulation material. So that's one of the ongoing projects where we are really trying to bring such advanced technologies to the market. And that brings me to the end of my presentation. So thank you very much for your attention.
Thank you very much, Roel. Very, very nice presentation and great examples of innovation in the facade design. Thank you everyone for joining us today for the webinar. We still have 3 other webinars left in this series. So next week, we will be doing the sustainable transport topic, and the following week, circular economy. And then the last day of October, it will be heritage, culture, communities, and sustainability. And you can book your places for the next webinars through the Engineers Ireland website. Thank you very much for attending this Construct Innovate webinar.